great
Jump.
with Eve.
We did it.
We shook the
We'll
world.
talk about that after we turn off the camera.
We shook the
Anyway,
world.
argument regarding
We shook the world.
continuity
You
At-
know
and endpoint. I was very surprised. I thought it was going to be closer.
what? The energy?
So, argument regarding continuity at an endpoint, okay? So, the math purist perspective is this, that if the limit doesn't exist if I cannot approach it from both sides briefly, okay? Yeah? So, the other mathematicians believe that that doesn't necessarily have to be true for a limit to exist. So, what they believe is for a function to be continuous at a right endpoint A or a left endpoint B, either of these two things have to be true. Okay, so for example, this guy right here is actually a right-handed endpoint because it's an endpoint on the right-hand side of the curve, right? This is the left-handed endpoint because it's on the left side of the curve. You understand? Yes? Sort of? Okay, so either of these things have to be true. So one of them is the limit as x approaches, let's say A. So that's a right-handed endpoint. We're talking about this way, right? So what's the only way that I can approach it from? From the left, right? So that's what it would be. Should equal that function now. If those two things are equal to each other, then we can say that the limit does exist at that value. You understand? And therefore it would follow the next one where they would be equal to each other, and then we would have continuity at that end. So either that has to be true, or the limit as x approaches B from the right, this is a left-handed endpoint, I can only approach it from the right, has to equal f of B. Okay, and because Ale, there is this discussion regarding the two ideas on the actual AP exam, they would not ask for continuity at an endpoint because they know that there's two different perspectives. There's two different views on this, and they don't want to create a problem. Because then you're going to get kids that are going to say, yes, it's continuous, and give them reason for it. And you're going to have kids that are going to say, no, it's not continuous, because that's how they were trained. Okay? But just understand that there are two different views on this. And both are correct. It just depends what kind of a mathematician you are. What kind of mathematician are you? You're a purist? A beginner?
Trash.
Trash. You're not ready to decide whether you are this or that?
Oh wait, I need.
You need to explore the world of math?
I decided to mathematician.
Math is all around us.
Rip.
Oh, I need big.
I love math. Math is
I
beautiful.
said
Did you
beautiful.
want to be like a math teacher?
No one says.
I always wanted to be a math teacher,
No one
yes.
says. I love that.
Since I was
love
in
math.
elementary.
Like when we make a
You wanted to be a
SWAT.
math
Did on
teacher
eight
since you were in
there.
elementary?
Like when
Yeah.
we did the SWAT or
It's
something.
legit, man. Look at
Other
this
than that, I
job.
want to be a fire truck.
Job is lit, man.
Not a firefighter.
It's a dance and sing.
I want to be the fire truck.
Learn what's up, you know, with modern society, you know, because I'm always with the in crowd, you know. I know the lingo, you know, like, oh man, this is lit, you know. Major L, major W, you
I
know.
don't want to be what?
It's just dumb.
Oh, you haven't learned that one
It's
yet?
just dumb.
You're a little behind, it's okay.
It's not.
There you go, there you go, you teacher, man. All right,
Wait, are they all on?
okay, so let's look at this next example. And let's see what happens here, okay?
Feel the burning.
So, on this one we have x to the 1/3 plus 2. What does the plus 2 make the graph do?
Go up to.
Go up to, right? What does x to the 1/3 look like? It's kind of related to x to the 3rd. You know what x to the 3rd looks like? Looks like this, right? The cubic function, okay? But this one's x to the 1/3, so it actually becomes what?
Like sideways?
Like sideways, right?
Yeah.
Kind of sideways like that?
Yeah.
Yeah, so this was x to the third, and this is x to the 1/3, right? This was x squared, and this is x 1/2, right? It's actually just half of it, right?
Yeah.
Because that's the square root of x, but if I put plus or minus, then whoa, now I have both of them. You understand? Cool? Alright, so let's draw this guy here and see what it gives us. You ready? So he's going to move 2 units up, 1, 2, and he'll look like this. Hold on. Let me make sure. I'm thinking of something, but I think it's... Yeah, okay. So he'll be like this. We'll come from the bottom, cross there, and then go like that. Cool? Good? Seabass, you awake?
Yeah.
Alright, making sure. So let's look at this graph and let's talk about it a little bit, okay? So, what's happening on the left side of 0? What's the concavity there? This side of the graph is concave what? Up, right? Concave up, like a cup. How about on the other side? That's concave what? Concave down. Like a frown, right? Okay. Where does it look like it changed the concavity? Where did it change from concave up to concave down? At 2, which is actually at what x? 0, 2, right? Okay, so could we say that it changed form at 0? At that point, 0, 2. Did it change its form? It changed from being concave up to being concave down? Okay, so when something changes form, the word that describes that, or the word that describes that is called an inflection. Okay, when I have an inflection, I'm changing forms. Yeah? That's the definition of the word inflection. But this is also a what? Starts with a P and ends with oint. A point. Okay? So if we put those two things together, what would we call it?
Inflection.
An inflection point, or a point of inflection, right? So it's a point where the graph changes its form. Very good. And that's exactly what it's called. Okay, so this is called a point of inflection. What does that mean? It's a point where the graph changes concavity. Or more generalized, it's where it changes form. Pretty cool? Do you know what will tell us where we have points of inflection? Not a horizontal tangent line, but it's actually called the second derivative. Okay? The first derivative tells us where we have critical numbers, right? And where we have maximums or minimums. The second derivative will tell us where I have points of inflection. So it'll tell me where the graph is changing concavity, right? When I find the second derivative and I do a sign line for it, the signs of the second derivative are actually telling me the concavity in that interval for the original graph. So like if from 5 to 10, I get a negative value in my sign line for the second derivative, it means that from 5 to 10, the graph is concave what? Down, because it's a negative value. You understand? Now if it changes from negative to positive in the next interval, then that means that at this number right here, 10, we have a point of inflection, because it changed from concave down to concave up. You understand? Kind of like when the signs changed, when you were doing the first derivative sign line, it meant you had either a maximum or a minimum, depending on how the signs changed. Here, it doesn't matter how the signs change. As long as they change, then you know for sure you have a point of inflection. Cool? We'll get into that later. Right now, I'm just throwing in random stuff just to blow your mind. Cool? Alright, so looking at this graph, the first question says, is it continuous at 0? So looking at it, is it continuous there? Yes? Okay, so let's prove that it is. What's the first thing? Must be defined, let's go. F of 0, what do we get? 2, it is defined. Step 2, the limit from the left must equal the limit from the right. So the limit as x approaches 0 from the left must equal what? What is the number? As I approach from the left, I get 2. Okay, what would the limit from the right be? 2. So I'm going to put equals the limit as x approaches 0 from the right. Therefore, we can say that the limit as we approach 2 from, not 2, just kidding, 0 from both sides is equal to 2. Okay, Liam? So now the third thing that we have to check is that those two values are equal, are they? We have to write it down, so we say f of 0 is equal to the limit as x approaches 0 of f of x. Now we can write our final therefore statement, which is f of x is continuous at x equals 0. Cool? Alright, so the next question is asking is it differentiable at 0? So it's asking, if I find the derivative and I evaluate it, will I get a number? Yes? Well, let's look at the graph again and think about the tangent line, right? So I have my tangent lines here, right? When it's concave up, they're below. And then what happens as I get closer and closer to that value? What do you think the tangent line is going to be at exactly 0? Vertical again? And then it's going to do what? Change this way, right? Okay, so let's draw that vertical tangent line. So is it going to be differentiable there? Can I get a derivative value at 0? No. What is the slope of that tangent line that I just drew? Undefined. So is it differentiable there? It should not be. Let's prove that it isn't. Ready? Alright, so we're going to need to find f prime at 0. What's that going to be? Oh, let's try to find f prime of x, sorry. What's the derivative of the original function? Can we do that? Alright, let's go. Hurry! 1/3 x to the negative 2/3? And that's it. Okay, can I rewrite it? So that's 1 over 3 cube root, very good, of x squared. Awesome, I'm so proud of you guys. Okay, now we need to evaluate it and find f prime of 0. So that's going to give me 1 over 3 cube root of 0 squared, so that ends up giving me 1 over 0, which is undefined. So was our theory and our idea correct just by looking at the graph? Yes, so can you, by looking at graphs, determine where something is differentiable or not? You should be able to, right? You got to think of it as tangent lines, and you were looking for where the graph has what kind of tangent lines? Vertical tangent. Cool? So let's write it down. F of x is not differentiable at x equals what? 0, because thank you. Because f prime of 0 is undefined. Okay, so what happened in this case? This function was what? This one was continuous, but not differentiable. Orally. So can we kind of throw out the idea that continuity implies differentiability?
We can't do it.
We can throw it out? We found a non-example, right? As long as we find one time that it doesn't work, that means it's not true, right? Okay, so this function was continuous, but it was not differentiable. So continuity, just because something is continuous, doesn't mean it's gonna be differentiable at that value. You understand? Was it differentiable at other places? How did I find the derivative at other places? Yes. Was that the only place that it was not differentiable at? For this graph? Yes, that's the only place that I would end up with a vertical tangent line, right? Everywhere else I wouldn't. Okay? Got it? Alright. One more example. This is x to the 2/3 plus 2. Right, so this graph is actually going to look like this. It's going to move 2 up, and it's going to be kind of like a bird. Or you can imagine Michael Phelps doing the breaststroke, and he's like,
That's fly, sir.
or whatever. I'm not a swimmer. Any swimmers in here? Yeah?
I wasn't swimming.
Show us the stroke.
I'm not down.
Will you show us?
Like pretty please?
Pretty please?